All right, here's our presentation on symmetric quantum homomorphic encryption. My name is Michael DeVos.
Henry Wero.
What we'll be going over is obviously the quantum homomorphic encryptions, a bit about what they are, inherent problems and research, definition, and the schemes we went through for our analysis. Now the QHE, the definition, first we have to go through what homomorphic encryptions are. Now if you ever heard about blind computing, it's about being able to encrypt the data, send it off to someone else, have them run computations on it, and then have it sent back to you, and you can decrypt it and get the end result as if those computations were done on the original data. Now for fully homomorphic, that allows not just a specific limited set of computations to be done, but all possible sets of computations on the quantum circuits. A difference between the classical and quantum for this, though, is that classical versions, they didn't have to worry about extra pieces for the quantum mechanics, obviously. There's one set of computations as opposed to computations with specific circuits and gates as inherent to the quantum homomorphic encryptions. Now, the 4 steps generally for all these algorithms, for these schemes, are the key generation, encryption, evaluation, and decryption. The key generation, we're doing symmetric key encryption, so there's just one single public key. But then there's a required private key for evaluation purposes, not for decryption. One key for encryption and decryption for that. The evaluation key is required to associate specific sets of quantum gates and quantum data for the evaluation to enact or correctly handle the encrypted data. The evaluation method itself handles the computations on that set encrypted data in the end.
So I'll talk about inherent problems and limitation. We have the quantum system is not equal to the sum of all its parts. And then you have the non-cloning theorem, whereby the system has to decrypt the whole data in full instead of doing it in streams. We have the Pauli errors brought about by conjugation of the circuits, and then the current limitation, especially the no-go result theorem, which shows the quantum mechanism alone is not insufficient to accomplish certain tasks. Next we go to my mic.
Compactness. For compactness, it's the one single definition we have to go over for our analysis. The compactness is a property required for fully homomorphic encryption or quantum fully homomorphic encryptions to exist. Not only does it have to work for all possible computation sets, but the complexity has to be independent between the decryption method and the evaluation method. So if evaluation is getting or scales with the complexity of the quantum circuits, decryption isn't affected by that. If that says such, then we say it's compact. If otherwise, if they're dependent on each other or they affect each other, then they're not compact.
So we talk about the current problems represented in this paper. So we have the issue of incomparable between EPR and AUX. And then you have the degrades of the T gates by the EPR. And then we have the issue of the evaluation of the auxiliary bits, qubits, being in polynomial exponential in their depth, so as to minimize the issues. Next we go to the scheme. So in the scheme we talk about the design of the CL, which is a Clifford. So it has the symmetric key encryption, and then it exhibits a quantum indistinguishability chosen plaintext attack security property. It is a compact quantum homomorphic scheme for stabilizer circuits. Clifford conjugates Pauli operators to Pauli operators, and then is a building block for EPR and AUX. So its advantage is that it's simple, simply because it's a base case. An advantage, one of the disadvantages is that because of conjugation of the circuits, Pauli errors occur, and then it's key-dependent evaluation. Next, we go to the EPR. So EPR is similar to the Clifford, whereby it has an symmetric key encryption, and then it uses a scheme called entangled quantum register to solve the T-gate correction problems. And then the decryption procedure scales with the square of numbers of the T-gates. And then it also exhibits the QIND CPA security property. Its advantage is that due to it being compact, it allows decryption scaling with complexity. And then its disadvantage is that it's not compact due to the issues described above, and it is dependent, key dependent evaluation. Next we go to the AUX. Its design is also similar to the two schemes mentioned. That is, it has symmetric key encryption. It uses auxiliary qubits to handle T-gates, and it exhibits QIND CPA security property. Its advantage is, one of the advantages is that it uses a higher advanced mechanism to solve the problems of Clifford, and then its efficiency in utilization of circuit constant number of T-gates. Its disadvantage is that it's key dependent evaluation.
Now the next two schemes, or last two, they don't have names, so just paper 2 and paper 3 schemes. Like the other ones, symmetric key encryption. Now this one, to handle the errors that propagate just from natural quantum mechanics here, using the T-gates to get the universal set to be computed, they utilize a quantum error correction code, embedding and appending that to the encryption, and a T-gate teleportation method, which allowed for copies of data to help find probabilities of where the corrections were located within the qubits. This one also exhibits the Q and CPA property. It's a defined security property out there. You can check it out. And then it also added on an entropic security quality. So like the other ones, this one's compact. It's a possibility for fully quantum homomorphic encryption status. And then it has improved efficiency for certain circuits. Those ones are related to if the evaluation circuits being used are of a constant number of T-gates, then it sees an improved efficiency as opposed to CL. This one is, this one is disadvantages is related to how it handled the error correction. That extra bit of algorithm to handle those errors requires more memory, more state, and a lot more computation. It requires quite a bit of a slowdown to keep up, or to analyze everything there. Now with paper 3, this one didn't have as detailed analysis, so we did our best to analyze in relation to the criteria that we're using across them all. It exhibits symmetric key encryption again, but this one uses a quantum one-time pad encryption, which allows for perfect security, but it did not analyze how it would handle the errors and T-gate errors. It was left for other papers to find as such a method to handle that. This one itself had a key-dependent evaluation, though, and it was not compact, so no hope for fully quantum homomorphic encryption status. Now, our general analysis, we had a few different methods for T-gate correction, the extra bit of information that was used for stabilizer circuits for the CL, entangled quantum registers for EPR, auxiliary qubits for the OX one, the OX one, and then paper 2 kind of used a mix of EPR and OX. The error correction code is similar to the auxiliary qubits. T-gate teleportation is quite similar to the entangled quantum registers. Now, paper 2 was the only one that had a key independent status for evaluation and compact. The only one that was coming upon possibly being a fully homomorphic encryption scheme, but it wasn't universal, and so it's still needing some work there.
So to conclude, much work is needed to stabilize the fully quantum homomorphic encryption scheme. So many schemes have been designed to solve these issues, but there is still it limits still knows and have yet to be proved or disprove whether or not a fully quantum homomorphic encryption scheme is feasible. That's the end of our presentation. Any questions?